A comet just erupted near the sun, and now a massive solar storm is racing to meet it on a collision course. In the next few weeks, Comet C/2025 R2 Swan will make its closest approach to Earth in recorded history, just as the sun unleashes its mightiest flare in months. This cosmic alignment is incredibly rare. We have a volatile comet, a powerful solar eruption, and a front-row seat from Earth. What happens when a solar storm meets a cosmic visitor? Let's explore this extraordinary scenario together.
First light. The outburst begins.
Comets are notoriously unpredictable, but what happened on September 26 caught everyone by surprise. Just 2 weeks after its closest pass to the Sun at a perihelion of 0.5 astronomical units, Comet Swan suddenly roared to life. Initially, it was a faint object, but amateur astronomers in Japan and Australia noticed a dramatic surge in brightness overnight. This wasn't a minor flicker. The comet's brightness leaped by a full magnitude, from 7.4 to a peak of 5.7, pushing it into naked-eye visibility under dark skies. What caused this? As the comet swung away from the Sun, intense solar heat penetrated its frozen nucleus. Pockets of sublimating cryovolatiles like frozen carbon monoxide and carbon dioxide buried for millennia reached their breaking point and exploded through the crust. This outburst ejected a massive cloud of gas and dust, dramatically expanding the comet's atmosphere, or coma, and feeding its enormous tail. According to cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory, such outbursts provide a rare glimpse into the primordial material from which our solar system was formed. This event signaled that Swan's inner engine was now exposed, making its next moves completely unpredictable, and turning it into a prime target for skywatchers worldwide. The sudden release of energy was so significant it altered the comet's light curve, deviating sharply from all predictive models.
Anatomy of a tail.
This isn't just a faint smudge in the sky. We're talking about a structure wider than 5 full moons laid end to end, stretching over 15 million kilometers through space, and its design tells a story. Comets actually have 2 distinct tails, and Swan's outburst put both on magnificent display. The first is the dust tail. It's broad, curved, and shines a pale yellow as it reflects sunlight. It's made of heavier micron-sized particles that are pushed gently by solar radiation pressure and tend to lag behind in the comet's orbit. The second, and more dramatic, is the ion tail. This tail is a narrow, straight ribbon of electric blue, composed of ionized gas like carbon monoxide ions, or CO+, which fluoresce brightly when excited by solar ultraviolet radiation. This glowing stream is blown directly away from the Sun by the solar wind at speeds exceeding 400 kilometers per second, acting like a cosmic windsock. As noted by comet expert Carl Battams of the U.S. Naval Research Laboratory, the ion tail is a perfect natural probe of interplanetary conditions. With Swan's tail now stretching across a huge patch of sky, it has become a perfect natural laboratory, exquisitely sensitive to the solar storm that is now heading its way.
The Sun awakens.
Just as the comet was putting on its show, the Sun, which had been quiet for weeks, decided to join the party with its most powerful eruption in months. On September 28, at 0843 Universal Time, satellites from the GEOES network detected a massive spike in X-ray emissions, jumping from a background level of 1 × 10 to the -6 to 6.4 × 10 to the -5 watts per square meter. An M6.4 class solar flare had erupted from a magnetically complex sunspot group designated Active Region 4232, then rotating into view on the Sun's southeastern limb. M-class flares are the second strongest category, and a 6.4 is a significant event powerful enough to cause radio blackouts on the sunlit side of Earth. Scientists at NOAA's Space Weather Prediction Center, like lead forecaster Dr. Alexei Pevtsov, immediately began analyzing data from the Solar Dynamics Observatory's AIA instrument at multiple wavelengths, including 131 angstroms, to assess the flare's power and, more importantly, what it threw into space. The energy release was equivalent to millions of hydrogen bombs detonating simultaneously. The timing was incredible. Just 2 days after the comet's own eruption, the Sun had fired a warning shot into the exact same quadrant of space.
Plasma on the move.
A flare is just the flash of light. The real power is in the billion-ton cloud of magnetized plasma it can hurl into space. And this one wasn't aimed at us. Within minutes of the flare, coronagraphs aboard the SOHO spacecraft, specifically the LASCO C2 and C3 instruments, confirmed that a massive coronal mass ejection, or CME, had been launched. This wasn't just a puff of smoke, it was a colossal bubble of solar material and magnetic fields, with an estimated mass of, well, about 1 trillion kilograms, racing outwards at a staggering speed between 800 and 1,000 kilometers per second. Forecasters at NOAA's Space Weather Prediction Center, using the WSA-Enlil prediction model, quickly charted its trajectory. The verdict: Earth was in the clear, but the CME was barreling directly towards the region of space now occupied by Comet Swan and its magnificent sprawling tail. Solar physicist Dr. Angelos Vorlidas, a leading expert in CME imaging, confirmed the CME's broad 90-degree angular width made an encounter highly probable. A rare and potentially violent collision was now inevitable within 48 to 72 hours.
Magnetic scissors.
So, what happens when a comet's tail, which is a magnetic structure, meets a massive magnetic cloud from the sun? Sometimes things just snap. This phenomenon is called magnetic reconnection, and it's one of the most explosive processes in the solar system. A comet's ion tail is made of plasma, held together by magnetic field lines streaming away from the sun. A CME, however, is a tangled web of powerful magnetic fields, often containing a strong southward-pointing component, known as the Bez field. If this southward Bez field, with a strength potentially exceeding 20 nanoteslas, slams into the comet's oppositely directed magnetic field, they can't merge. Instead, they collide, break apart, and explosively reconnect into a new shape. As space plasma physicist Dr. James Drake has explained, this process converts magnetic energy into kinetic energy with incredible efficiency. When this happens, the energy release can be immense, acting like a pair of magnetic scissors that cleanly severs the entire ion tail from the comet's head. This is called a disconnection event, and it can happen in a matter of minutes, leaving the old tail to drift away as a new one begins to form.
The forecaster's puzzle.
Predicting this collision is more complex than it sounds. It's like trying to predict if one puff of smoke will hit another in a hurricane. While models from NOAA's Space Weather Prediction Center, like the Enlil heliospheric model, showed the CME's main lobe sweeping through Swan's sector, CMEs expand, twist, and deform as they travel hundreds of millions of kilometers through space. Hitting a relatively small target like a comet's tail is not a guarantee. The biggest challenge for forecasters is the lack of direct measurements. Since the CME is not aimed at Earth, we won't get in-situ data from satellites like the DSCOVR spacecraft, which normally act as a warning system by sampling the solar wind a million miles upstream from us. Scientists must rely on images from spacecraft like SOHO and Stereo A to refine the CME's trajectory and predict the exact time of impact. An error of just a few degrees in the initial launch angle can result in a 10 million kilometer miss by the time it reaches the comet. The best estimates place the arrival between 48 and 72 hours after the flare. But the question remains, will it be a direct hit, a glancing blow, or a near miss?
Citizen science mobilizes.
When a cosmic event like this unfolds, the big observatories aren't the only ones watching. A global network of backyard astronomers becomes the front line. Professional telescopes have schedules booked months in advance, so they can't always drop everything to watch a single event. But citizen scientists, however, can provide continuous round-the-clock coverage. This is crucial because a tail disconnection event can be incredibly fast, unfolding in less than 2 hours. An amateur astronomer with a modest setup, like a 10-inch reflector and a modern CCD camera, could be the first person to capture the collision. Organizations like the Association of Lunar and Planetary Observers, ALPO, have entire sections dedicated to coordinating comet observations. Renowned astrophotographer Damian Peach has shown how high-resolution amateur images can rival those from professional instruments. These observers are not just taking pretty pictures, they are collecting valuable scientific data, or photometry, that can be used to measure brightness changes and map the tail's structure with incredible detail, helping to build a global record of this rare encounter.
The perfect alignment.
As if a volatile comet and a perfectly aimed solar storm weren't enough, the celestial geometry for this event is almost unbelievable. On October 21, 2025, Comet Swan will make its closest approach to Earth, passing just 0.25 astronomical units, or 39 million kilometers away. That's roughly 100 times the distance to the Moon. For a comet with an orbital eccentricity of 0.98 and a low inclination, that's an exceptionally close flyby. This proximity makes it an easier target for even small telescopes. The timing is equally perfect, coinciding with a new moon, meaning the sky will be at its darkest. But there's more. On that same date, a hypothetical interstellar visitor, 3I Atlas, reaches a superior conjunction on the other side of the Sun. As orbital dynamicist Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory would note, the probability of a dynamically new comet like Swan and an interstellar object aligning so closely in time and space is vanishingly small. This alignment provides a unique chance to compare a native solar system body with an interstellar one under the same solar conditions, a rare convergence of a dynamic comet, a potent solar storm, and an ideal observation window from Earth.
Southern skies, spotlight.
For these crucial weeks, the best seats for this cosmic show are in the southern hemisphere. From major observatories like the Siding Spring Observatory in Australia to backyard setups in South Africa and South America, Comet Swan will be high in the sky after sunset. Its path takes it through the southern constellations of Grus and Piscis Austrinus, passing near the bright guide star Fomalhaut. Viewers can use this star as a guidepost to locate the comet, which will appear as a fuzzy star with a long, faint streak extending from it. Even a standard pair of 7x50 binoculars will be enough to reveal the tail, stretching over 2.5 degrees, the width of 5 full moons. For those in the northern hemisphere, the view will improve throughout October as the comet climbs higher in the western sky after midnight. The checklist for observers is simple: find a dark sky, use a star chart to locate the comet, and watch for any changes. By taking images every few minutes, observers can create time lapses that will reveal the tail's motion and any sudden disruptions caused by the solar wind in stunning detail.
Cosmic forces collide.
Here's the bottom line. We have a comet that has just undergone a massive outburst, making it unusually active and producing a large, dense tail. We have a powerful M6.4 flare that launched a CME racing directly towards it at nearly 1,000 kilometers per second. And we have a historically close and well-timed approach to Earth, giving us a perfect view. This sets up a documented encounter between a solar storm and a comet's ion tail, a phenomenon that could cause dramatic changes, with spectral analysis potentially showing Doppler shifts in ion velocities of up to 50 kilometers per second. It's important to be clear, as a scientist from a program like the NASA Comet Observation Database would emphasize, the comet's initial outburst and the solar flare are a coincidence. The sun did not cause the comet to erupt. However, this coincidence has created a rare opportunity for both professional and amateur observers to witness the powerful dynamics of our solar system in real time. The key results are still unfolding, written in gas and light across the night sky, a cosmic experiment for the entire world to watch. We are witnessing a truly unique cosmic alignment, a volatile comet, a powerful solar storm, and a front-row seat from Earth. What will happen when the CME slams into Swan's tail is still unknown. Will it be a gentle ripple or a dramatic disconnection that severs the tail completely? The only way to find out is to look up. This is a rare opportunity for anyone with a pair of binoculars or a small telescope to contribute to a global science campaign. The universe is putting on a show, reminding us of the immense and unpredictable forces at play. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech.